Our last speaker is Ting. Ting got her PhD from University of Wisconsin Medicine, and before joining University of Washington biostatistics as assistant professor, she did her postdoc in the Department of Statistics in Wharton. And Ting will talk about, again, Mendelian randomization. So I will let you yourself to read the title. Okay, Ting.
Thank you so much, Peng, for the nice introduction, and thank you for inviting me to talk here. Today, I'll speak about a simple cure for bias from weak instruments and horizontal pleiotropy in Mendelian randomization. And it's a great pleasure today to talk about this because I think it's a very beautiful solution for bias, for tricky biases. This is a joint work with Dr. Junsha and Dr. Han-Sang Kang from University of Wisconsin Medicine. This is the outline of today's talk. First, I'll introduce instrumental variable and Mendelian randomization. And then the focus of today's talk will be about debiased inverse variance weighted estimator in summary data Mendelian randomization. And specifically, we will talk about how the DIVW estimator deals with many weak instruments and balanced horizontal pleiotropy. I believe the audience should be pretty familiar with the concept that association is not causality, but I just want to show an interesting story here. So studies have found that dog obesity is associated with human obesity, but common sense tells us that intervention on dog does not reduce dog's owner's weight. So there's no causal effect. And the reason behind this little story is that the dog's weight and the owner's weight, they are not causally related, but they can be related by a lot of, through a lot of unmeasured confounders, such as lifestyle. So in the language of linear regression, suppose this exposure variable is related to you and the outcome variable is also related to you, but there's no causal effect of X on Y, then we will still observe the association between X and Y. So this is sometimes called spurious association if we do not properly account for you. Instrumental variable is a powerful device to deal with unmeasured confounding. And we have heard a lot about instrumental variable from Carlos and Zhonghua's talk, so I'll be a little brief here. So when we think about these three instrumental variable assumptions, it's helpful to think about a prototypical instrument, which is in randomized encouragement trial. And suppose we want to learn the effect of vaccine on some outcome of interest, then in a randomized encouragement trial, we can use the random encouragement as this instrumental variable Z. And if the encouragement is effective, then we should be able to see that this Z is related with X. So this justifies the relevance assumption. And for the second assumption, because Z is randomly assigned, so it's supposed to be randomly, it's supposed to be independent with the unmeasured confounder. So it justifies the second assumption. And in terms of exclusion restriction, it requires have no direct effect on outcome Y. So if this random encouragement is blinded, then there is some justification that the Z does not have direct effect on Y unless it successfully changes the status of X. This instrumental variable is a powerful device to disentangle causal effect from unmeasured confounding bias. But in practice, instrumental variables are very difficult to find. There is a recent concept starting somewhere in 2003 called Mendelian Randomization, and says we can use the genetic variants as instrumental variables to study the causal effect between complex traits. So the reason behind Mendelian basis behind Mendelian randomization is that because from large GWAS study, we already know a lot of genetic variants that are related to the BMI, for example. Then those genetic variants can be used as instrumental variables. And also because we randomly inherit the genetic variants from our parents, so it's reasonable to consider that the genetic variants are independent with the unmeasured confounder U. And if also these genetic variants, they have no direct effect on the outcome, then we are all good. We can use this genetic variance as instrumental variables. So in summary, Mendelian randomization is a method that uses genetic variance, also known as single nucleotide polymorphisms, aka SNPs, as instrumental variables, to assess whether a modifiable exposure X exerts a causal effect on the outcome in the presence of a measure confounding U. And in this talk, I'll use genetic variant and SNP and IV exchangeably. In Mendelian randomization, a particular design is called two-sample summary data Mendelian randomization. And it combines publicly available summary data on SNP exposure and SNP outcome associations from two separate studies. To give an example, suppose we want to estimate the effect of BMI on the risk of CAD using 1,119 independent genetic variants, then we can find two data sets, the exposure data set and outcome data set. In the exposure data set, we use a GWAS for BMI, for example, in the UCAL bank. And in the exposure data set, we will have this marginal association statistics, gamma J hat, which is the effect of this ZJ on the exposure and the standard error sigma XJ. And analogously for the outcome data set, we have a GWAS for CAD in another consortium. And we observe the marginal association statistics denoted as capital J gamma J hat and the variance and the standard error sigma YJ. So these two data sets are independent because they cover non-overlapping samples. To see how the data looks like, usually we have a lot of genetic variants. Here we have 5, and here I only show 5. And then, so we record this little gamma J hat for each SNP and its standard error, and the capital gamma J hat for each SNP and standard error. To see how we can use these summary statistics to identify causal effect, it's useful to start from linear structural equation. Although these linear structural equations are not needed for our results, but it's useful to gain some intuition. We start from this exposure equation called in 1, which relates the exposure variable to this instrument and also a measure confounder. And in the second model, it's outcome model, it relates the outcome to the exposure variable and some measure confounder, some random error. So notice that the Z does not appear in outcome equation because we assume the exclusion restriction. So the Z does not have a direct effect on the outcome once we have accounted for X. But this will be relaxed later. But for the main part of the talk, let's assume that assumption. And then we just plug in equation 1 to equation 2. So we obtain a so-called reduced form that relates the outcome Y to this instrument ZJ, and its coefficient is capital gamma J, and we know it's beta 0 times little gamma J. This motivates the following assumption. So this little gamma J is assumed to be normal centered at little gamma J, and the capital gamma J hat is assumed to be normal centered at beta 0 times gamma J. And this approximation is good due to large sample sizes and independence of the genetic variants. And notice that beyond the linear structural equation, this is still a good approximation because if Y is binary and follows a logistic model, then this beta 0 is a conservatively biased estimate, is a conservatively biased parameter for causal odds ratio. And outside these parametric assumptions, we can interpret beta 0 as a local causal effect. And because of this assumption, then naturally we can use their ratio. So the ratio denoted by beta J hat, which is the ratio of capital gamma J hat and little gamma J hat. And it's supposed to be well centered around the beta 0. But this is using only genetic variant J. Now we have P genetic variants, so we can use all of them. Then a natural idea is to use the inverse variance weighted estimator that combine all these ratio estimators, and then the weight is their inverse variance. So this estimator is originated from meta-analysis. But in this particular setting of Mendelian randomization, empirical evidence shows that the IVW estimator is biased when we have weak instruments. And to mitigate the bias, practitioners usually pre-screen for strong SNPs using the genome-wide significance p-value, which is 5 × 10⁸. However, I think this is at most a banded solution because it does not resolve the bias, it only mitigates the bias. Now, I'm ready to talk about the 2 salient challenges in Mendelian randomization. So the first challenge, we have already talked a little about this. It's many weak instruments. So it says that each genetic variant is only weakly associated with the exposure variable X, but we have a large number of such genetic variants. And second is the widespread horizontal pleiotropy, which basically means the exclusion restriction assumption can be violated because the genetic variant can have effects on the outcome through other pathways, not mediated by this exposure variable X. And in Mendelian randomization, it's crucial to deal with these 2 challenges simultaneously for good practical performance. There are existing works, so for the sake of time, I will not go into detail, but I just want to highlight the MR-REPS method that's proposed recently in 2020. And MR-REPS is robust to many weak IVs, and it's also able to deal with balanced horizontal pleiotropy, but all the rest of the methods, they sort of only deal with one of these challenges. So we have MR-REPS, which is a great method, but it's relatively complicated because we need to deal with an optimization problem based on a profile likelihood function. And it's not necessarily it's not guaranteed to give us a unique solution. So in this talk, we will introduce a one pill cure. So it's a very simple solution to these 2 challenges. Now let's move on to the main topic, the main part of today's talk, the DIVW estimator. So first, I'll talk about 2 assumptions. Assumption 1 says that this marginal association statistics follows a normal distribution, and this is reasonable due to large sample size in the GWAS study. And the second, and the 2 sample design will guarantee us that this data from the exposure data set and the outcome data sets, they are independent. And then because of the mutual independence of Z1 to ZP, it's reasonable to assume that these 2 × P marginal association statistics, they are mutually independent. And we assume these standard errors are known, which is also reasonable due to large sample sizes. And we consider that this capital gamma J equals beta 0 times little gamma J, which basically assume no pleiotropy for now, and this will be relaxed later. And the second assumption says that there exist positive constants to bound this ratio of standard error. And to see what this means, we can write the formula of the standard errors and write their ratio. Because each genetic variant can only explain a very small proportion of the variance in these complex traits, then we can use the variance of X divided by variance of Y to approximate this part. So basically, assumption 2 is reasonable as long as the sample sizes in the 2 data sets are comparable. So in summary, assumptions 1 and 2 are reasonable for both common and rare variants. And here I need to talk about a key concept called IV strength, which we will use to derive the asymptotics, to characterize the asymptotics of the estimators. So here we define mu J, which is this effective little gamma J divided by the standard error. This is the Z-score of IVJ's effect on the exposure. So this characterizes 2 notions of weak IVs. First, this little gamma J can be small. And second, the sigma xj can be large, which is most likely due to rare variant. And when IVs are strong, this mu j square is of order the sample size nx. And if IVs are weak, this IV strength can be much smaller than the nx, or even can be of constant order. And if the IVs are irrelevant, we have this mu j square equals 0. But this individual IV strength is not so crucial here. What's crucial is the aggregated IV strength. So here we define an average strength of the IVs, which is denoted by kappa. This kappa, again, can range from 0 to the order of sample size nx. And the kappa can be estimated very easily using the average of f statistic -1, denoted by the kappa hat. Now we are ready to characterize the asymptotics of IVW and see why, where this bias, weak IV biases come from. So we divide the asymptotics into 4 regimes. So in the first regime, it's the only regime where the IVW estimator is consistent and asymptotically normal. It says that we need this IV strength kappa divided by P go to infinity, and we also need the number of IV goes to infinity. And this is a technical Lindenberg condition. And so this is the only regime where IVW is consistent and asymptotically normal. And in the second regime, if we only have the average IV strength goes to infinity, then the IVW is consistent. And if the average IV strength goes to a constant, then it's biased towards 0 because it will converge to something that's something smaller than 1 times beta 0. And if the average IV strength kappa goes to 0, then the IVW estimator will converge to 0. And in typical MR setting, we usually are in the regime C. So this is why we usually observe the IVW estimator being biased towards 0. In summary, the IVW estimator is consistent and asymptotically normal only when all the IVs are strong in common variance and we have the sample size large compared to the number of IVs. Let's take a closer look at the IVW estimator. First, we notice that the expectation of the numerator equals negative beta 0 times some positive quantity, and it's not 0. So that explains why that means the IVW estimator is not well centered at the parameter we want. So this source of this non-zero expectation is because of the measurement error in this little gamma j hat. And we can also see that the asymptotic bias of the IVW estimator can be written as something like this. So it's of order negative beta 0 divided by kappa plus 1. So this explains why the IVW estimator is biased towards 0 in 2-sample Mendelian randomization, and why the consistency of the IVW estimator requires kappa goes to infinity for this asymptotic bias to goes to 0. And finally, the consistent and asymptotic normality of the IVW estimator will require the asymptotic bias divided by the standard error goes to 0, so which is exactly kappa over P goes to infinity. But we still do not want to give up on the IVW estimator yet because it's popular, it's widely accepted, it's very easy to understand, and it can be computed very fast. And it always has a unique solution compared to optimization-based methods such as the MRFs. So motivated by all this, we propose a beautiful solution to the weak IV bias of the IVW estimator called D-bias IVW estimator. So the D-bias IVW estimator is like this. So compared to the IVW, the only difference is in the denominator. So we modify this denominator by subtract sigma xj squared. So it turns out this little modification makes the D-IVW estimator well-centered at beta 0. So this can be seen from here. A little calculation will show that the expectation of the numerator now is exactly 0. We can also study the asymptotics of the D-bias IVW estimator. So the first regime says that if this average IV strength kappa times root P goes to infinity, then the D-bias IVW estimator is consistent and asymptotically normal. And if we only have this condition holds without the Lindenberg condition, then it's still consistent. So compare with the IVW estimator, the D-bias IVW estimator is consistent and asymptotically normal in regime A, B, and C from theorem 1, whereas the IVW estimator is consistent and asymptotically normal only in regime A. And recall that I said in typical MR settings, regime C is most common. So this means that in common MR analysis, the IVW estimator is biased, but the D-IVW estimator has really good property. And the variance of the DIVW estimator has an explicit form, so can be consistently estimated. A little more about this condition. So this condition is likely to hold in MR analysis. For example, if all the IVs are weak in the sense that each z-score is in the order of 1, then we only need such weak IVs. The number of such weak IV goes to infinity. So incorporating many weak IVs into DIVW can improve its performance, whereas incorporating many weak IVs in IVW can make it biased. So this condition is also imposed by other methods that are robust to weak IVs, for example, the limo estimator and the MRFs. And this condition can be checked by this quantity that can be calculated from data. Now we are ready to deal with the second challenge, the pleiotropy. We still start from the linear structural equation, and notice that here we have the z in the outcome model, which means the zj has a direct effect alpha j to the outcome. And we still plug in equation 1 to equation 2, and then we know that this capital gamma j now equals beta 0 times little gamma j plus alpha j. So previously we assume alpha j equals 0. And we assume a assumption that allows pleiotropy. So basically we let this allow this capital gamma j being of this formula, but we need to restrict the direct effect. And the restriction we impose is the balanced horizontal pleiotropy, which assume these direct effects are RID normal with mean 0 and is independent with the IV strength little gamma j. So so here I'm ignoring the theorem, but we show that the DIVW estimator is still consistent and asymptotic and normal, but its variance will be larger because of these random direct effects. So now I'll show some simulations. To closely mirror what's done in practice, we take the real BMI-CAD data set available in the package as our simulation parameters. We have, let's ignore the selection data set for now. So we have a exposure data set we already seen and an outcome data set. So exposure is GWAS for BMI, outcome is GWAS for CAD. And this is the result. So notice that the DIVW estimator can be very easily implemented using basically just one line of code. And this gives us the results. So in case 1, we have many weak IVs and no null IVs. And we have more than 1,000 IVs, and we use all of them. And the average IV strength is now 7.78, which is of constant order rather than going to infinity. And we have this condition that's 260, which is relatively large. And so we see that the DIVW estimator has mean 0.4. 0.4 is the truth and has great coverage probability, close to 95%. And all the other estimators, so IVW, MR Agar, MR median, MR mode, they have some bias. So the IVW is biased towards 0 and with poor coverage probability. And comparing the DIVW estimator with MR reps, so the performance is basically very similar. So we can achieve the performance of MR reps using a very simple solution. That's the DIVW estimator. And in the second scenario, we consider many weak IVs and many non-IVs. So basically, we only have 100 relevant IVs, and the rest more than 1,000 IVs are irrelevant. So the average IV strength is 1.05, which is very small. And this condition is 35, is relatively large for DIVW to work well. So we see the performance still very good and comparable to the MR reps estimator. And finally, the application, we apply the method to the BMI and CAD data set, and we use all these more than 1,000 SNPs, and the average IV strength is 6.78, and this condition is more than 200. So the DIVW estimator says that the BMI has a significant causal effect on the CAD, and the estimate is around 0.365. And so for the other estimators, they are within 2 standard errors of each other, but we can clearly see that the IVW estimator is biased towards 0. and DIVW has similar performance to the MRS. So we also have a diagnostic tool for the assumption 1. So it's very simple. We just calculate a standardized residual. And if all these assumption holds, then the standardized residual should follow a normal distribution. So we can plot this QQ plot, and it shows the normal approximation should be a reasonable approximation, should be reasonable. So take-home messages. The IVW estimator is biased in presence of many weak IVs, and the IVW estimator plus screening does not solve the bias. It's at most a band-aid solution. And we highly recommend the IVW in MR as a baseline estimators. It is as simple as the IVW with explicit form. It is a simple cure for bias from many weak IVs and balanced horizontal pleiotropy. And there's no pre-screening required. Instead, many weak IVs are helpful for the DIVW estimator. And this is not an end, but a start. So the DIVW estimator can serve as the baseline estimator for investigating more complex settings. And this is our paper, and we have a R package on GitHub. And so please feel free to try it. And finally, so I just quickly use 1 minute to go through this slide. So previously, we assumed that the direct effect, the pleiotropy, follows a balanced horizontal pleiotropy assumption. But if we have more complicated pleiotropy, which is basically if this direct effect, they are correlated with the IV strength, little gamma j, then this is the correlated pleiotropy, which is a very challenging setting in Mendelian randomization. And we have a new work called GENIUS-MAWII estimator, and it's able to deal with the correlated pleiotropy. And from this real data analysis, we investigate the effect of BMI on these blood pressure. And we see that the GENIUS-MAWII estimator has a point estimator that's close to 0.14, and the standard error look like this. So compared with all the other estimators that are based on balanced horizontal pleiotropy, we see their estimates are larger compared to GENIUS-MAWII, probably because they fail to account for non-zero direct effect of the SNPs. And also MR Agar has a point estimator that's similar to ours, but its standard error is quite larger compared to our standard error. So in fact, in this case, if using the MR Agar, we will fail to conclude with statistical significance, but here we will be able to. Thank you so much for listening. This is all I want to talk about.
Okay, thank you, Ting, for this wonderful talk. So we can take one question. Is there any question for Ting? Maybe people are hungry or tired. So if there's no question, we can stop here. Okay, yeah, thank you, everybody.
Thank you.